I want now to talk about the applications. So there was something very influential a while ago called AG, Aldai-Gayotto-Tashikaba correspondence. And it's often called the first instance of a 4D, 2D correspondence of some four-dimensional quantum physics to two-dimensional, maybe conformal field theory correspondence. And by now there are many variants, and depending on how you think about it, you can formulate it as a physicist, you can formulate it some more geometrically, you can formulate it maybe more interesting for topologists. And I can tell you a few things I do know, and I can state a few more theorems that relate that somehow illustrate the other structures in VOA language. Why don't we start with our Y, the Y algebra? So, and this has a geometric interpretation and a physics interpretation. So, the geometric interpretation is the following: you take just a three-dimensional complex space, so that you should think about as a very simple example of a three complex dimensional Calabi-Yau, and then you choose a divisor in there. So you choose you choose three embeddings of a C2. For example, C1 is the one where you just set the first coordinate to 0, C2 the second one, C3 the third one, and you choose a divisor, and let's call it N1 times the first one, N2 the second one, N3 the third one. So in here, and then the geometer is interested in what is called spiked instantons. So that's the moduli space of coherent sheaves supported on such a divisor. And well, that's what it is. And and now the question is, in this setting is, can you? So this means it's interested in geometry here, the moduli space of certain sheaves. And the question is, one takes then an equivariant cohomology of that's a huge vector space, and asks whether there acts something naturally on it. And these are then usually called in physics BPS algebras, in this setting cohomological Hall algebras, and so on. Now, what again, this Rabczak that I wrote down together with three further collaborators, Seubelmann and two people from Melbourne, whose names I forgot. There's so many names around. They understood that on this, the geometric action of this cohomology Hall algebra on this moduli space of sheaves gives rise to an action of a vertex algebra. Which one is it? The Y algebra, right? The Y N1, N2, N3. So a nice, let me write Rabczak et al. I think he was also the leading force. Okay, I might be wrong with this. I shouldn't say that so loudly. This is the problem with the recording, right? Everything I say will stay forever. So anyway, I know a lot from him. That's why I'm saying that. So they showed that these Y, N1, N2, N3 algebra at psi, so psi is related to certain parameters here appearing, acts on this equivariant cohomology of coherent sheaves supported on this divisor. Now, and this is a general thing. More general, what one wants to do is one wants to look at moduli spaces of instantons, some geometric structures on toric varieties. So this would be kind of the trivial example for that. And there's a huge idea around how you can relate to a toric variety a VOA. I will not, anyway, and eventually you would like to prove that it's not just this combinatorial relation between toric variety and VOA. This is something not deep, but it's deep in the sense that indeed there exists a moduli space of something that one would like to call G instance on this toric variety, carries naturally an action of the vertex algebra, of a certain vertex algebra. That's what one wants to go, and the only case that is understood is this case, and for the other cases there aren't even conjectures around, so or they are fairly weak, so it's not really worth talking about it. Okay, now how do we think about this? So I hope it's okay that I just talk now. How do we relate this to physics? So you really, I think at the moment, so when I was your age, it was always string theory, string theory, string theory. That was why people are interested by what the mathematician wanted from physics, and the physicists hoped that this was the thing. Wasn't it like this? Okay. Or are you too young for that? Maybe. Anyway, nowadays it's QFT, four-dimensional quantum field theory. So the string theory, there are still string theories, they are still good, doing good things, but their connection to physics is not that happy anymore, just because at least that's my impression. But what happened is that now quantum field theory, really what we want to what a physicist wants to understand is a particle physics wants to understand four, right? You don't necessarily need to understand a string theory in 6 dimensions. You need to understand what is happening in space-time. And now the program is 4D. 2D correspondences. That's the slogan. So you want to study 4-dimensional quantum field theories that are maybe not totally realistic. So this is, if you give a talk to a physicist, you always get very quickly criticized. Yeah, this is not a realistic thing. Anyway. But at least they are well studied. You can well study because they have well-defined, so in a mathematical sense, invariance. That could be of a geometric nature, it could be of a topological nature, or a VOA nature, and usually, in fact, all of all three. Now here in this case, the setup of instantons, one thinks about it as a setup in a string theory, a certain brain setup in a string theory on C3. And then what do people like to do in physics? They like to compactify down to smaller dimensions. In fact, they have a procedure that compactifies this D-brane setup to 4 dimensions. And then you can think about it as having a 4-dimensional quantum field theory in 4 dimensions. And then these divisors, you think about it as in 4 dimensions. Your divisors become codimension 1 planes, so 3-dimensional planes that intersect diagonally, all 3 there. And these two C2s, these 3, 1, 2, 3, these 3 C2s, they become 3-dimensional planes intersecting diagonally, and the degree of the divisors on each one becomes the rank of the gauge group of the 3-dimensional of the 4-dimensional quantum field theory that lives between 2 such boundaries. So this means one thinks about it, and now we have a problem to think 4-dimensional and projecting down on 3-dimension. So we just project everything on the plane, on the whiteboard, and so we think about the setup being our 3-dimensional planes intersecting diagonally, and then we have here our 3 regions, our 3 interfaces. On each interface there lives a gauge theory with gauge group UN1, UN2, and UN3. And these 3 and this, so on the boundary 3 dimension, you always think about as you have a topological field theory, and then the 3 boundaries, they intersect in 2 dimensions, and 2 dimension always, depending on your taste, calls for VOA or CFT. And now, the relevant paper here is, it's called Vertex Algebras at the Corner. By Gayotto and Rabchak. They studied this physics setup, and they told us what do we have to associate to this, and they made one observation, namely a Y has a nice S3 symmetry. Rotate, you can reflect, right? And but they were also able to translate this into statements of associated VOAs, right? It is the VOA. So here you have something sitting. It's maybe you give it an order. You say you start from here. So it's a Y, N1, N2, N3 algebra, depending on the coupling constant of the gauge theory. So this becomes the coupling constant of the gauge theory, the psi, and you have this sitting. Well, of course, I can look at the setup by just rotating a little bit, right? And it should be the same type of theory. But if I rotate it, I would get the Y, N3, N1, N2 algebra, and maybe the rotation also involves a change of coupling constant somehow. Apparently it does. So they had a physics reasoning to define the Y algebra, and the definition was exactly the cosets that I wrote down and that are not on the board anymore. It's also not that important, but whatever it is, it should be a 2-dimensional, a vertex algebra that depends on the 3 labels, and so it should be, and that should be some meaning that it has representation categories of type UN1 and UN2, UN3. And anyway, it turns out, so what you do is you take a Lie superalgebra of type one label slash the other one, for example, N1 slash N2 or N1 slash N3, and then you take a nilpotent element that has an affine subalgebra involving the remaining label as subalgebra. For example, if N2 is less than N3, then I could take an affine Lie algebra of type N1 slash N3 and take a nilpotent element that has an affine subalgebra of type N1 slash N2, so that I can take the coset of that, and that is a possible definition. Anyway, they have a few pages because it takes time to set all this up, and they have a dictionary of what corresponds to what, and but one thing is, and then their conjecture was, well, the algebra at the corner of these interfaces does not depend on how you look at it, so it doesn't depend on S3, and that's the motive. That was a main motivation from physics for proving these theorems. I'm also not good with names, mentioning names. One of my absolute major collaborators is Andy Linshaw. He's excellent, and we have developed a program of what we like invariant theory of vertex algebras in general over the last 10 years, and this theorem was then eventually our highlight. So.
Could you say a little bit more about what the vertex operator algebra acts on?
Yeah, and now from the physics perspective, or the
geometric point of view, or whatever viewpoint you like.
Yeah, and I think it's always good. I'll start. Let me start with one theorem, maybe, and then we can continue from there. Okay. Yeah, so Jörn's comment is good because having a vertex algebra there, well, okay, you have it there, but it should give you something meaningful, right? And so there's this original AGT correspondence so the original AGT correspondence, maybe or a version of it, is the case n2 and n3 both equal to 0. From the vertex algebra point of view, this corresponds exactly to the principal W algebra, so the special cases of triality I started my whole session with this afternoon. And so the paper by Rabczak et al. That connect these Y algebras to this moduli space of spiked instanton is in some sense not good because it only says that the algebra acts, but not whether it does it in any meaningful way, right? Because if I want to say that a vertex algebra acts, well, it acts on any vector space that has the same dimension as a module of it, right? So, for example, if I think about an affine algebra, well, its vacuum Werner module is the polynomial ring in negative variables. So, if I have a vector space that is just this polynomial ring, then I automatically have an action on that. So, it could be a meaningless statement. And I don't want to say this is a criticism on this, but it's exactly your question, how to make this better. You want to prove that the VOA does not only appear there, but in a meaningful way. And there's a really nice theorem. This is, I think, one should take this as the guiding theorem. So it's by Schiffman and Wasserow. It's maybe roughly 10 years old. And let me just phrase it here with a little bit more detail. So it's here the spiked instantons are in this case coherent sheaves on CP2 with some can be identified with some coherent sheaves on CP2 with some framing at infinity, whatever that is. So let me write this down. Of rank R with a framing at infinity along a CP1 if you set one of your coordinates to 0. The first statement is it is a module for the principal W algebra of GLR. So that is that's good. But now we also want to so this means the W algebra acts on the equivariant cohomology, the equivariant cohomology of the moduli space. That's also true here in general, and that is something. That is promising to show further, but now you want this action to be meaningful. So now it becomes, I think, most important. So the next statement here is the fundamental class of this cohomology is a Whittaker vector, and let me write Whittaker/Gayotto vector, because Gayotto deserves so much credit that one should that he is here now mentioned here. The fundamental class of this cohomology is a Whittaker vector whose norm is Nekrasov's instanton partition function. I will comment on the words of this on the vocabulary in a moment. So thank you. Yeah.
And do you fix any of the topological types?
Of
There's C1 and C2.
um,
Turn classes.
yeah, and so
Yes, I don't think it's connected. Is it lie in the framing in infinity?
Yeah, I don't know the answer, but I think you do fix it. So let me say. So the fundamental class is naturally graded by the second Chern number.
Okay.
That gives it a grading. So this means really, this vector. So this is first of all a very famous theorem. Now, what do we have here? This cohomology is acted on by the W algebra. In fact, the cohomology is naturally a Verma module. Which Verma module, which weight labels, or which central character, it depends on certain parameters that you fix. Then you have the fundamental class. And now the whole module is naturally graded by second Chern number. And it turns out the fundamental class is not a vector in the module, but in the completion. And so if you, right, it's an infinite sum. Anyway, you have a natural pairing on the module via correspondences, which allows you to take the norm. The norm becomes then a formal power series because it's an infinite sum. And you have to take a graded sum, somehow graded by a parameter, which you probably should call h bar. So this means this graded norm is a power series, a function, and it's called Nekrasov's instanton partition function because from the physics point of view, it's the partition function of the instantons in the four-dimensional field theory. So that's the physics relevance. From the geometric point of view, it's the norm of this, let's call it the graded fundamental class. And from the VOA point of view, it is a Whittaker-Gayotto vector. So let me tell you what a Whittaker-Gayotto vector is, because we haven't had it. That's also something you usually don't learn in the first VOA course. So usually we like to have a highest weight vector. Remember, for example, for the Heisenberg VOA, we wrote down this ket lambda, and it had the property that it was annihilated by all positive modes. The zero mode acted as our by weight, and the negative freely. Here, a Whittaker vector is an eigenvector for the positive modes. So for example, a Whittaker vector for the Virasoro algebra of weight lambda is where the positive one mode acts by multiplication with lambda, and then you would still need to define that all, actually, so for the Virasoro algebra, this is the most general Whittaker vector you can write down. The one mode acts by multiplication with lambda. The two mode acts by multiplication with mu for your favorite scalars lambda and mu, and all higher modes annihilated. And now you can generalize, right? For these other W algebras, you have certain conditions. Anyway, and it turns out these vectors, if you look at a normal module of your vertex algebra, Verma module, for example, you have no chance to find it because you just have no chance to find it. But if you go to the completion, if you allow for infinite sums, then it's not that hard to find those. Okay, and so this means so Whittaker vectors are elements not in a module of a vertex algebra, but in formal power series with a parameter. I think often people use a capital lambda for that parameter. And so this means the Whittaker vector, let's call it W for Whittaker, is a sum lambda to the n Wn like this, where these Wn's live in certain graded subspaces. And in these cases, it will in fact be exactly the subspaces of corresponding conformal weight. And then the Whittaker vector Schiffmann-Wasserau talk about has actually the eigenvalue for the corresponding positive mode lambda, this formal parameter. Now, if you have this Verma module, this Whittaker vector is naturally identified with the fundamental class, naturally graded by second Chern number. And now you have a pairing, you have a geometric pairing, and you have a VOA pairing, just by pairing with a Whittaker vector of the dual, of the contragradient dual. And the statement is that the geometric pairing is the VOA pairing, and both of them give you a power series in lambda, and this power series in lambda is also the partition function of Nekrasov, well-known physicist, and that's the statement of the theorem. And this is where and in fact there has been a whole I mean, this has now become also very interesting in various respects to now also study this more fancy types of vectors in modules of vertex algebras and W algebras. And the state of the art of the AGT correspondence in more generality is, for example, well, one can show that there is somehow a natural action on these equivariant cohomologies of W algebras, but the Whittaker vectors, I mean, the generating vectors are still open. One has to do it. Doesn't seem that easy. Okay.
What is the question? The question is whether the fundamental class
Yeah.
provides a Whittaker vector?
Yeah, or generalization. There are then further variants. Gabriele knows about that. There are. Then, in fact, a lot of things one can do is now. There has been a very much related proposal, maybe 3 years ago, by Boris Fagin and Sergei Gukov, and they call it a VOA of M4.
I have a question.
Yeah.
So you had your theorem, neutrality. Why doesn't such a theorem follow from this kind of result? Or is it only one of those?
If you mean from a result of this one?
Yeah.
In fact, I even overstated it. They constructed an action of a W algebra that conjecturally coincides with this one. So I actually overstated that. But still, also their construction depends on the ordering of the labels, because it's so even their construction is not totally obvious that the symmetries holds. But I also overstated this a bit. Okay. So now, as this is a general picture, and so in general, you would like to say I take my favorite type of four manifolds, let me say a smooth four manifold. I take my favorite type of gauge group, a compact Lie group, and now I'm interested in equivariant cohomology of moduli space of G instantons on it, whatever it is. And the slogans is always it wants to be a module of a VOA. So and this VOA is determined by the gauge group and the four manifold. So you want to attach, in particular, you want to attach VOAs to 4 manifolds in hopefully a meaningful way. This is not far developed. So far we only have one paper, maybe a second one by Boris and Sergey, and they have this idea is they somehow would like to have meaningful invariance of smooth four manifolds together with a choice of compact Lie groups. And their idea is I take my 4 manifold, it might have some boundaries. Well, anyway, the 4 manifold has an associated VOA. Each 3-dimensional boundary component is labeled by a category, a full tensor category of modules of the VOA. And moreover, you can glue 2 4 manifolds on a common boundary to get a bigger 4 manifold by corresponding gluing of the VOAs along the tensor categories. So if you draw a picture, what we would like to have is I have no idea how you draw a 4 manifold. Anyway, 4 manifold looks like this for me. So you have your 4 manifold, and it might have a boundary component, and boundary components you give label it by categories. I mean, the 4 manifold itself is labeled by a V for VOA. And now if you have and now we give it extra indices 1 for that is the first one. We can have a second one. And so here we would have a category C2, for example. And now you would like to ask, can you glue these together on the common boundary to get a bigger 4 manifold? And the idea is, well, also the boundaries, they have some kind of orientation. And you can also give categories an orientation because these are braided tensor categories. And in a braided tensor category, you can always take the same category, same tensor category, but you can give it a second braiding, namely the inverse of the original one. And you should think about it as the categorical analog of reversing orientation. You call the category with the inverse choice of braiding the reversed category, the category reversed to C. And so this means this glued manifold should be a vertex algebra associated to V1, V2, and C1 and C2. And let me there's a nice theorem that that physicists understand extremely well, and it says the following. So V1, V2, VOAs, C1 and C2 categories of V1 and V2 that are nice enough. And so nice enough means in particular we need rigid, and semi-simple shouldn't be necessary, but we can't prove better at the moment. And they are vertex tensor categories. I don't write it out. And now assume you have an isomorphism between the irreducibles of these 2 categories, a linear isomorphism, just between the set of irreducibles object. If you have this, then you can write down just the sum over all irreducibles in one of them, object times their images under this linear isomorphism. I mean, it's just a linear. I'm sorry. It's just an isomorphism of these sets. It's just the isomorphism of the sets. So then you can ask yourself, can you give this one? You also require the additional condition that the image of V1 is the V2. And under these 2 conditions, this thing here is a VOA itself if and only if there's a braid reversed equivalence. Equivalence C1 equivalent to C2 with the opposite choice of braiding, let's call it this equivalence F, such that F is equal to tau on the irreducible objects. Right, so this this theorem you prove it just by in a categorical. So it turns out that bigger VOA extensions one can prove are the same thing as commutative algebras and tensor categories, and so proving this theorem becomes very, very nice. It's just a purely categorical statement. It becomes all of a sudden just provable. And so this means, what this statement means in this four-manifold lecture, two four-manifolds can be glued along a common boundary to a bigger four-manifold if and only if the categories they are labeled by coincide, just that on one of them I chose the opposite orientation. It means I have the reverse braiding. So it's a really nice, I like this so much because this is a really good VOA theorem actually, at least for me. And it is the VOA illustration of the gluing procedure of four manifolds. So it's something nice. Okay.
And are there any constraints on the boundary parts to this four manifold, or are you gluing it along arbitrary three manifolds?
Yeah, we have to ask Boris and Sergey for that. In fact, I think they are at the moment promoting this picture, and they give examples of V1s and V2s. If we take G to be SU2, and that's it. But I have one more. Shall I present one more property in this one? So why not? I have 4 minutes. So one more thing that people like is to blow up things, right? So in this original AGT correspondence, one could blow up a singularity, and there was a well-known statement that this Nekrasov partition function of the blow-up is equal to a certain infinite sum of products of instanton partition functions, where the whole parameters are related in a certain way. And if one wants to think about this in terms of the Schiffmann-Wasserow theorem, well, the instanton partition function is given by norms of Gayotto vectors and on certain modules. So there should be a procedure that maps a module of the W algebra to an infinite sum of tensor product of modules in such a way that the Gayotto vector, the Whittaker-Gayotto vector of the module becomes an infinite sum of Whittaker-Gayotto vectors of the on this big thing. And then Boris and Sergey proposed a much more general notion of blow up. This means this is done by taking some kind of smash product of 4 manifolds with a CP2 bars. And the idea is that the VOA associated to the smash product is nothing but the old VOA times the urod. So urod is a Russian word meaning freak, ugly person, I don't know, something very unpleasant. Well, Boris, he came up with that name, and he likes that name actually a lot. Anyhow, so I have 2 minutes, and I will write down one theorem and one formula that illustrates this, and it's exactly, it is absolutely, it's totally the blow up on the VOA level. It's so let me be very explicit. We had the statement for SLN we had that the diagonal action is this W algebra. This can be a phrase that that the and I'm not now specific with what this labels means, but it means that this big algebra is a sum of modules of the affine subalgebra and a commutant, the W algebra, and it's a certain infinite sum going over, in fact, over the root lattice. Over dominant weights that lie in the root lattice. I can do this thing also, but replace the SLN by my favorite module. The effect I get, in fact, is that I get then here. I have to add here everywhere a label mu somehow, because now the weights somehow, the modules that appear also depend on this choice. It's not that important what the explicit formula is. Now, what do we do is we have our quantum Hamiltonian reduction of the VOA, and it gives a module. And so let's just define the quantum Hamiltonian reduction of the module of weight mu to be equal to the W algebra module that has exactly this weight label. All right. So the VOA blow-up equation is, I can replace W on both hands side here. So what it means is, what did I do here? Here on the first line, I did the quantum Hamiltonian reduction on the first factor at level L-1. On the second line, I did it on the first summand at level L. So I did two very different quantum Hamiltonian reduction. I did two very different cohomologies. Even the central charges of associated VOAs are different. But it turns out this is an isomorphism of vertex algebras without conformal element. So you remove the conformal element, and it's also then an isomorphism of modules. In particular, what it means is you take your fundamental the cohomology of this instanton space is such a module. You multiply it. That means you tensor it with the U-rod. The U-rod is nothing but this affine VOA at level 1, and all of a sudden this tensor product is this huge different sum. But each summand here can be identified with the equivariant cohomology of a certain instanton space. The weight labels then label certain parameters that you fix. And so in particular, if you fix a highest weight vector in here, a Gayotto vector in here, you automatically get an infinite sum of Gayotto vectors here, whose pairing then automatically is the pairing here, the instanton partition function, the pairing of highest weight vector with its dual, that is the number 1, and here you get the infinite sum of the two. So, it's really, even if you enjoy what you enjoy, but it's kind of nice that there are different areas. So there's one area, and I will conclude now. There's one area at the top, it's called physics. It's the one that has the good ideas, and then you can translate it either to geometry, and I told you a little bit how the geometry comes into the game. You can also, here now, so you also would like to simply think about it more topological, just invariance of manifolds as such. It seems the art is, well, you try to understand as much as you can in each direction, and maybe you can translate the statement that you like in the language that you do understand and prove it there. So that's the message. And so this means if you like these areas, then you should better try to understand as much as possible. The message I wanted to bring with this last hour is that, once one understands a lot, one can prove the VOA statements that are analogous to what other areas tell us. And that's a lot of fun. Anyway, I want to say thank you, especially to those that came from so far away. I'm quite impressed. So we have participants from the US, right, and from South Korea. But I, of course, thank you all for coming. I was very happy to be here for this week. So thank you very much. Your encore. Cesar.
Well, so I just want to say thank you very much to you, Thomas, for an excellent series of lectures here.